Hey kiddos, today we are going to move on to rotation. So what is a rotation? It is a transformation in which a figure is turned about a fixed point called the center of rotation. Rays drawn from the center of rotation to a point in its image form the angle of rotation. Okay? A rotation about a point P through an angle of x degrees maps every point Q in the plane to a point Q prime so that one of the following properties is true. So if Q is not the center of rotation P, then QP is equal to Q prime P, and the measurement of angle QP Q prime is equal to x degrees. And if Q is the center of rotation of P, then Q is actually equal to Q prime. You can rotate a figure more than 180 degrees. This diagram below here shows a rotation of points A is 130 degrees, 220 degrees, and then 310 degrees. So that's 130 degrees, and that's 220 degrees, and then that's 310 degrees. About the origin, which is the point in the middle. Point A is it, and its images all lie on the same circle. A rotation of 360 degrees maps a figure onto itself again. Use coordinate rules to find the coordinates of a point after a rotation of 90 degrees, 180 degrees, or 270 degrees about the origin. So today we're going to be talking about rotation. This is probably it's a little bit more complicated than translation and reflection, but y'all can handle this. All right, so what we have here are some coordinate rules for rotations about the origin. So basically here are some shortcuts to use. When a point, okay, is rotated counterclockwise, so clockwise is this way, like that's how a clock rotates. Counterclockwise is the opposite way, counterclockwise. So when a point is rotated counterclockwise about the origin, these rules are true, okay? So for a rotation of 90 degrees, your point would then become negative BA, which notice the order switches and the Y value becomes the opposite. For a rotation of 180 degrees, if you have a point, notice the location of the values stay in the same spot, but they both become the opposite. And for a rotation of 270 degrees, that point becomes the order switch again, so the values switch places, and the X value becomes its opposite. So these are our shortcuts that we'll be utilizing for this. All right, another concept is rotational symmetry. When the figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure, this point is the center of symmetry. The rotation can be either direction, whether it be clockwise or counterclockwise. So looking at this example here, the regular octagon has rotational symmetry. The center is the intersection of these diagonals, so you can see that right here. The rotations of 45 degrees, 90 degrees, 135 degrees, or 180 degrees about the center all map the octagon onto itself. So the regular octagon also has a point of symmetry, which is 180 degrees of rotational symmetry. For a figure with S lines of symmetry, the smallest rotation that maps the figure onto itself has a measure of 360 degrees divided by S. Okay, so for example here, the triangle has line of symmetry right here. So these are the lines of symmetry, which we've talked about when we talked about translation. It has 3 lines of symmetry can be drawn for the figure. So the equilateral triangle has 360 degrees divided by 3, or 120 degree rotational symmetry. So that's basically how we can solve for rotational symmetry whenever a figure has lines of symmetry that we can actually identify. All right, so for this first example, we're going to rotate a figure in the coordinate plane. So notice I went ahead and I graphed the quadrilateral RSTU with these vertices, okay? And what we're going to graph now is its new image after a 270-degree rotation about the origin. This is where these shortcuts really come in handy here. So all I'm going to do first is I'm going to figure out what are my new points, and then I can plot them. So according to the shortcut for 270-degree rotation, and notice this is a counterclockwise rotation that we're going to make, I would follow this shortcut, which basically tells me that I'm switching the order and I'm making the x its opposite. So for the first point, r prime, switch the order and make the x value its opposite. So that's my first, that's r prime. S prime would become 1, negative 5. T prime becomes negative 3, negative 5. And U prime becomes negative 1, negative 2. Now all I have to do now is graph it. And this is what the new one would look like being rotated 270 degrees counterclockwise. Alright, so for this next example, we're going to graph the triangle ABC, which I've already done. And now we're also going to then graph its image after making a rotation of 180 degrees about the origin. So again, I'm using my shortcut to help me figure out what would be the new points. And according to this shortcut, for a 180-degree rotation counterclockwise, all I have to do to the x value and the y value is actually make them the opposite. So A prime becomes negative 3, negative 1. B prime becomes negative 3, negative 4. And C prime becomes negative 1, negative 1. Now I can graph that. And that is what it would look like once it's been rotated 180 degrees counterclockwise. Alright, so for this next example, we're actually going to perform a composition, which means we're doing more than one move. So I've already graphed RS, so it's 2 endpoints, okay? And we're going to reflect it across the y-axis, and then we're going to rotate it 90 degrees about the origin counterclockwise. So first with the reflection part, and we're reflecting over the y-axis. Notice I've already drawn the y-axis here in blue so you can kind of see it clearer. And if I reflect it over the y-axis, R prime moves there, and S prime moves here. So there's our new line being reflected over the y-axis. And those points are negative 1, negative 3, and negative 2, negative 6. So what we need now to do the rotation is we need to utilize what our shortcut is. And the shortcut is negative y comma x, which basically means what we're doing is we're switching the location of those points, and we're going to make y the excuse me. We're going to make y the opposite. Now, the points that we are changing are the r prime and the s prime, okay? So we're actually moving this one, not the pre-image here. So we're moving this one 90 degrees counterclockwise. So these are the points then that we're going to manipulate using our shortcut. So in doing that, we end up with negative 1 there, and that becomes positive. And then, so our double prime is 3, negative 1, and then S double prime so we'd end up with 6, negative 2. So let's go ahead and graph that. So after graphing it, this right here is where our final answer will be. Alright, so for this next problem, I'm actually going to let you guys do this one on your own. Oh, yo. So I just wanted to kind of talk you through it, though. First, you need to graph the original, the pre-image, TUV, triangle over here. And then we're going to do, again, it's a composition, so we're going to make 2 moves. This time, we're going to rotate it first about 180 degrees about the origin counterclockwise. And then after we rotate it, then we're going to reflect it over the x-axis. So these are the original points. Here's your shortcut, which means basically you're just making the x the opposite and the y the opposite, okay? So that will give you your brand new coordinates for your primes. Then, after you've done that, that's your rotation about 180 degrees. So wherever you end up, then that you'll reflect over your x-axis, which again, you can refer back to your previous notes to get the shortcut for that if you need it. If not, you probably should be able to directly draw the brand new one. All right, here we're going to be identifying rotational symmetry. So does the figure have rotational symmetry? If so, describe any rotations and map it. So first we're looking at a parallelogram. Now, we've talked about lines of symmetry. Now, just because it has lines of symmetry doesn't necessarily mean it has a rotational symmetry. So these lines of symmetry that we look for have to be from like a vertex to another vertex. So notice that's one line of symmetry that goes vertex to vertex. And then there's another line of symmetry that goes vertex to vertex. So because it actually works that way, then this one actually does have rotational symmetry. And to figure out what's the degree, we're going to take 360 degrees and we're going to divide it by the number of lines of symmetry, which were 2, and we end up with 180. So this has a rotational symmetry of 180 degrees. Now let's look at the trapezoid. If I look at the trapezoid from vertex to vertex, notice that's not a good legit line of symmetry there, and neither would it be on the other direction. I do see it does have a line of symmetry here, but it doesn't go to a vertex. Doesn't even start from a vertex to a vertex. So this is not a justifiable line of symmetry for discovering rotational symmetry, okay? So this actually does not have it. Moving on to the dodecagon. So again, let's see if we can find any lines from vertex to vertex. That looks like 1. That looks like 2. I think we got 3. But hold on, wait a minute. We actually have from these vertices 4, 5, and I believe I got one more from this vertex to this vertex. Wow, we got 6 for this figure. Okay, so yes, and to discover the degree, we'll do 360 divided by 6, and that gives us an answer of 60 degree. I'm going to let you guys do the octagon on your own. So let's move on to the right scalene triangle. Notice from you can't really draw one line of symmetry from like one vertex to another. So that's a no. Like I can't draw any type of line. I can draw like that line or this line, but they're not going into a vertex essentially. So yeah, that doesn't work. So that's a no. And then the arrow, again, I can't really here to here. No, that doesn't. Those don't work. That doesn't. I mean, that's a line of symmetry for that. This line here is a line of symmetry, but it's not the type of line to show rotational symmetry. So I don't see anything that works. So that's a no too. So here we have now an isosceles triangle, and kind of like the other triangle, I don't see any way. I mean, it has a line of symmetry, but that's not a rotational line. So this is also a no. Now, a basketball is very unique because, well, technically, doesn't really have vertices or vertexes like that in a sense. But I do know we can split the basketball like so. So therefore it does have, because it's round, it actually does have rotation obviously. It's the round figure. So it does have 2 lines of rotational symmetry here. So 360 divided by 2 means that its degree of rotational symmetry is 180. Looking at now, yeah, the next one is a guitar and guitar rotational symmetry. Yeah, that's a definite no on the rotational symmetry. But let's look at a card. Can a card possibly have a line of symmetry? Well, I guess if we go like that, that would fold one on top of the other, and I believe like so. So it's got 2 lines, kind of like the basketball situation there. So yes, 360 divided by 2, 180 degrees would be its rotational symmetry. Buenos tardes, adios, ciao.